So the enzyme is the lactate dehydrogenase. It does this step right here. So it's really pyruvic acid plus this gets converted into lactic acid, and lactic acid is now with the NAD+. So like link these two. These two are on the right side of the equation, and then pyruvic acid and NADH is on the left side of the equation. The reason why that's important is because when you make this new, you regenerate the NAD+, the NAD+ can now go back here, and you can now break down another glucose, okay? The point is that there's only so much of the NAD+. There's a finite number of NAD+ in your tissues. So if any of these things start to run out, you can't do glycolysis anymore. The rest of your body, to make new NAD+, you have to go through the electron transport chain, okay? So if you skip down to the notes in the chemiosmosis thing, you end up regenerating NAD+. Skeletal muscle, though, has this ability because it has this enzyme to take the NADH and remake NAD+, so that you can go back to glycolysis. Okay? So again, and just recheck your notes. It's pyruvic acid plus NADH gives you lactic acid and then NAD+. Then the question is, what happens to the lactic acid? Anybody know? Yeah, eventually your liver will convert it back into pyruvic acid, and then the pyruvic acid can be used to make other biochemicals. Because 6, normally there's 2, right?
Mm-hmm.
So you just take the number above and multiply it times 3?
Yes.
Okay, and let's see. 12 CO2s, it's a 12 carbon chain, that makes sense. 3 times 6 is 18, so 18 NADHs, yep. And you change that to 18 H pluses, which I agree with. Okay, and then 3 times 2 FADH2s, and then 3 times 2 is 6 there. Very good. Leave it up there for a second.
Why do you multiply by 3 again?
Oh, because
there's 6 acetyl-CoA, so there's 2 per carbon chain.
Okay.
If you take that, I don't know, math, it's 3 missing exponent.
you just take these with
Got it.
Well,
That's the way I think about it.
Okay.
so, or another way of saying it is, before we made 2 acetyl-CoAs, right, from the glucose?
Mm-hmm.
Now, you have a 12 carbon chain, and we're assuming that all those 12 can get turned into acetyl-CoAs.
Right.
Each acetyl-CoA is 2.
Mm-hmm.
So basically, how many acetyl-CoAs can you make if there's 12 carbons? It would be 6,
Mm-hmm.
right? So now that we have 6 acetyl-CoAs, that's going to be 3 times bigger than the 2 acetyl-CoAs that glucose would normally do.
Got it.
Okay? Does that make sense? And so we just took all the numbers that she did in the Krebs, which were accurate, and we multiplied them by 3. And this is kind of your check right here. Your check is this, 12 CO2s. Should there be 12 carbons from a 12 carbon chain fat?
Yeah.
And yes. Okay. This also tells you a really interesting thing, is that fat is very calorically dense. It has a lot of energy associated with it. It typically has twice the energy of carbs or protein. It's really high energy. We really can break down fats very efficiently. So when you go through ketosis, our body actually does that very well. You know, if you have fat reserves and you know, you start to break that down, the ATPs, I mean, you're going to make plenty of energy from a fatty acid chain. So kind of a big biohacking thing right now is fasting. So people will do a fast for like, I've been doing it for like a couple of years now too. I'll do like a 16 and 8, or sometimes I'll do a 20 and 4 or something like that, where you're just not eating. I mean, and 8 hours of it is sleeping, so it's not like you're not eating. And some people will do that though too. So you'll, like, for example, I'll like stop eating at 7 and I'll eat again the next day at 11 or whatever. So there's like 16 hours in that. And again, you just go through ketosis, you break down the fats, and it's just It's just kind of fun to kind of biohack your own body. Everyone's different. It may work for you, it may not, you know, so it's just kind of a interesting. Make sense? Okay. So when redox reactions take place, energy is released, right? When something goes from a high to a low concentration, energy is also released. Okay? Keep going.
So the energy released is used to combine ADP and phosphate to make ATP, and then oxygen receives 2 electrons and combines the 2 hydrogens to make water.
So we do make water in our metabolism, which is weird. Okay, so this is called metabolic water. Makes sense? There are some animals. I went to the desert like 10 years ago because I wanted to find this kangaroo rat. But the kangaroo rat, like, it's this rat that like hops on.
Used from high concentration gradients and low through ATP synthase, and energy is released. But if there are puncture holes in the or along the inner membrane space, the hydrogen would diffuse out of the cell, which would affect the energy
Out of the
release,
mitochondria,
or the
right?
mitochondria, yes, which would affect the energy release to make ATP. So therefore, there will be no ATP made.
And that's exactly what he found. So Mitchell did this in the 70s, way before you were born. But they didn't know what actually the step that directly caused ATP synthesis. So what they saw was that the electrons were still going down the cytochromes. You guys follow me, right? Down the cytochrome chain, but there's no ATPs. And really, and this is what Had just said, is basically you need to have that hydrogen concentration gradient. That last energy transfer of the gradient going, the hydrogen's going through the ATP synthase, that's the final step that's needed to actually make ATP. Okay? He actually got the Nobel Prize in, I think, '78.